Alright, so in this video, I'm going to be looking at the function f of x equals x minus 2 over x squared minus x minus 2. So what we're going to be doing in this video is we're going to identify where the horizontal asymptotes are, where the vertical asymptotes are. We're going to be looking if there's any holes in this function as well. So let me rewrite this function first by changing the denominator, by factoring it, and rewriting it. So this is going to be x minus 2 over x squared minus x minus 2 can be factored to x minus 2 times x plus 1. If you don't know how I did that, I just found two numbers that would multiply to negative 2 and add to negative 1. So that's the coefficient right there. So once I found those, that's negative 2 and positive 1, and I factored it. So the next thing to realize is that we have this x minus 2 and this x minus 2, and in the numerator and denominator, and they can cancel out. And so when they cancel out, we have the function 1 over x plus 1. So this thing, when they canceled out, this indicates to us that we have a hole in the function. So at x equals 2, we would have a hole in the function. That's one thing that we know, since we canceled this. We removed this discontinuity essentially. And we got this function. So this function is actually going to be equal to this function for all values except when x is equal to 2. So technically, one thing to note is that these two functions are not equal for all values. So x over 2, x minus 2 over x squared minus x minus 2. This is not going to be equal to 1 over x plus 1 because when we have x equals 2, this one's undefined. This one's undefined. And this one does have a definite point. So technically they're not equal to each other, but when we remove this discontinuity, we have a function that is continuous at x equals 2, and so we just remove that hole essentially. So we have this right over here, and so now we can try to find the vertical asymptote. So let's try to find the vertical asymptote. So the vertical asymptote is going to be where the x value is where the function's undefined. Here it's a rational function, so that's when the denominator is set equal to 0. And so that is at x equals negative 1. That's our vertical asymptote. Now let's try to find our horizontal asymptotes. So that's HA. This is vertical asymptote, horizontal asymptote. This is when we just find this by looking at the limit as x approaches positive or negative infinity of the function. And so what is this going to be equal to? Well, what I like to do is I like to divide by x here. So I'm going to divide the numerator and the denominator by x. This is not the only way to do it, but this is one of the ways. So this just gets you the limit as x approaches positive or negative infinity of 1. Let me write this a little bigger. 1 over x over 1, because x over x is 1, plus 1 over x. So this looks more complicated than it was originally, but as you will see, this limit as x approaches, let's do positive infinity. As x approaches positive infinity, this is going to become bigger and bigger. As the denominator gets bigger and bigger, the whole thing approaches 0. And even when it's negative infinity, it's still going to approach 0. Even with this, so it's going to approach 0. But just by knowing that the numerator approaches 0, we know that since the numerator is 0, we know that the whole entire limit is going to be equal to 0. So the limit as x approaches positive and negative infinity is equal to 0, indicating that we have a horizontal asymptote at that point. So that's at y equals 0. So yeah, we did a lot, right? We identified that there's going to be a hole at x equals 2, that there's going to be a vertical asymptote at x equals negative 1, and that there's going to be a horizontal asymptote at y equals 0. The reason why I use this function instead of this function is because these functions are going to be equivalent for other points except when x equals 2, because we're going to have a hole in this function, but in this one we won't. So technically, for other points, they are going to be equal, so they're going to have the same vertical asymptotes, and they're going to have the same horizontal asymptotes. So in that way, they are equal. So now that we have this all found, let's see if the graph of this function matches what we just found here. So let's scroll down. I have my graph right over here. And so we identified, let me actually write it out here. We identified that there's going to be a vertical asymptote at x equals negative 1. Was that negative 1 or positive 1? Yeah, that was negative 1. there's going to be a horizontal asymptote at y equals 0 and a removable discontinuity or hole. Let me do that in red. A hole at x equals 2. And let's see if that matches what we saw. So we see this vertical asymptote at x equals -1 right over here. We see this vertical asymptote right there. I'm not going to draw that to its entirety, but we see that right there. Let me scroll down a little. And we also see this horizontal asymptote at y equals 0. So we're getting closer and closer to 0 in both directions. So even here, let me do that. So even as we go here, as x approaches -infinity, we're getting closer and closer to 0, but we're not going to ever touch it. Even in this direction, as we go to positive infinity, we're getting closer and closer to 0. We're not going to touch it though. And then we have a hole at x equals 2. We do have a hole over here. So we do have a hole over here, but we cannot see it. There is going to be a hole though. This is in Desmos.com, and so we can't really see the hole. But when you kind of look at it, there is going to be a hole there at x equals 2. So that was kind of a fun little video about trying to find where the vertical asymptotes are of a function, where the horizontal asymptotes are, and just trying to look at the properties of a function. I hope you found this video helpful.